All right. Today you might need a calculator, and if you don't have a calculator, you can just use your phone or whatever. What we're going to be doing today is continuing our discussion of kind of the theoretical basis for statistical analysis. That's going to involve doing some calculations today. Like I said before, my goal for you is for you to understand how statistics operate, and so in almost all cases, the very first time we do stuff, we're going to do stuff by hand so that you learn what the process is, so that when the computer starts doing stuff for you, it's not a mystery to you what the computer is doing, because you could, if you had enough time, do those calculations by hand. We'd use the computer because oftentimes we're working with larger data sets and it just becomes cumbersome to do things by hand. So, as I have said before, the central limit theorem is central to doing statistics. This idea that if you take samples from populations, calculate sample means, the distribution of sample means, is normally distributed. Second idea that's really crucial is the empirical rule, which applies to normal distributions. And basically says that about 68% of the area underneath the normal curve is within one standard deviation. 95% is within 1.96 standard deviations of the mean. I've been telling you up to this point, it's about 2, and it is about 2, but it's technically 1.96, and this becomes important that you remember this particular number, and I'll tell you why that particular number is important when we get to that. The last thing that we need to think about is the idea of sample size. We talked about this last time, but I don't think I summed this up quite as well as I could have. With sample size, larger is generally better. Up to a point. And beyond that, adding sample size just requires more effort, more money, without giving you any increase in statistical power. That cutoff happens to be at about a sample size of 30. Now, the effective sample size we saw in the last class. If we have a population that looks like this, if we go and sample that population and we only take 2 observations, it gives us what begins to look like a normal curve, but that normal curve isn't particularly normally distributed, so it deviates from normality somewhat. And it's also really broad, covers the whole range of the original data for the most part. Bump it up to 4, the curve looks more normal, but it's also narrower and peakier in the middle. And once again, the average of the sample means is a good approximation of the population mean, which is, in theory, one of the things we might be trying to estimate. Sample size of 10, narrower and more normal looking. Population size of 30, very narrow and also very normal looking. So when we think about doing hypothesis testing, testing to see if two means are different, or to test if a particular parameter is different from a theoretical expected value, we need to think about two things. We need to think about the location parameter, which in this case is the mean, the sample mean. But we also have to think about the spread of the distribution of the data, which usually has to do with the variance, or the standard deviation, or the standard error of the mean, or a 95% confidence interval. These things are all measures of spread, the spread of the data. Okay? You could, in theory, use any of these to communicate to somebody how variable the data are that you're basing your sample mean on. So in order to tell whether two average values are different, you need to not only know what those average values are, but you also need to know how variable the underlying data that generated those sample averages are. And that's what we're going to talk about today to a large degree. So we typically ask these questions. Are two means different? Are two groups that we've looked at, gathered data on, are they different? We might also ask ourselves, is the value that we observe different from some theoretical value that we might have an idea of what the average should be? But in all cases, we still have to have a measure of the mean and some measure of variation. So this is just some data pulled off of a textbook's website. And in this case, we have three populations, the red population, or three samples, the red sample, the black sample, and the blue sample. And for each of these, the mean of those samples is shown as a vertical line. And you can see that the spread is different in each of these different populations. The blue is relatively narrow in spread. The red is a little broader in spread. And the black extends all the way from over here to all the way up here. And so the black population is really super variable. So for each of these populations, we might want to say, is the blue population different from the black population? Is the blue different from the red? Is the black different from the red? And in those cases, the variability obscures our ability to see differences between the means. Because if we go into this population, we take a sample of 10 observations out of it, it'll give us a mean that is somewhere in here, but that mean might be right where the population mean is. It might be a little lower, it might be a little higher. The degree to which it drifts up brings it closer to the black mean, and as a result, it becomes more difficult to tell those two means apart. In the same way, we could sample from the black mean. Some of them could be higher than the population mean, some of them could be lower. As this drifts lower, it gets closer to the red mean, which makes it difficult for us to see the difference. As it drifts above, it makes it difficult for us to tell black from blue in terms of means. So it isn't just the location of the mean, it's also the amount of variation. The black population has a really wide variation in the original population, which means that any given average that we calculate from that has the possibility to drift around quite a lot. So if we take a sample from this population, we need to have a pretty big sample in order to nail down the black means sample mean and have it correspond to that population mean. So if we don't have a large sample, this thing will tend to drift around, so our confidence about where the population mean is eroded. And so in order to encompass all of the sample means that could be drawn from this population, we need to widen our scale on the x-axis here so that we're sure that we encompass all of those sample means. So here we have the black population. Let me just draw it up here. it has a really broad distribution. If we go in here and we take 4 samples, they might correspond to the population mean or they might not. We come in and take 4 more samples. That sample mean may be way over here. Come in, take 4 more samples. The sample mean may be way over here. If, on the other hand, the original distribution, that's an ineffective eraser. If the original distribution was really narrow, taking 4 samples anywhere in here, they're all going to be relatively closely clustered. So the original spread of the data and the sample size that you're taking affect how big your confidence interval has to be in order to say, I'm 95% sure that within this range, somewhere in there is the population mean. Okay? So part of it has to do with the spread of the data. The other part has to do with how large your sample size is. The larger your sample size is, the better you are characterizing that population, so the closer that sample mean is going to be to the population mean. And so as you increase sample size, the distribution of sample means gets smaller and smaller, so your confidence interval around that population mean gets smaller and smaller. And so this is why sample size is important. Let me try an eraser that might not make the board all smearing. So how do we do this? Okay, maybe it's not the eraser, maybe it's the board. Let me try a different colored marker. So let's just make up a data set. So here is a data set, 4 numbers. Just pulled them out of my head. 2, 4, 6, 8, 10. In order to quantify a sample, let's say that this is a sample of something. Maybe it's the number of eggs that my chickens produce over 5 different days. In order to quantify this, we need a location parameter and we need some measure of spread. The location parameter that we typically use is the sample mean. This is just the arithmetic average of these things. How do we calculate that? Yeah. Add them all up, divide by the number that are there. 2 and 4 is 6, 6 and 6 is 12, 12 and 8 is 20, 20 and 10 is 30. We have 5 observations divided by 5. The average is 6. You can either memorize an equation that tells you this, or you can know how to do it, and then from that you could actually generate the equation if you wanted to. The equation for this is uppercase sigma, an x representing each of the x values. There's an I because this is observation 1, observation 2, observation 3, observation 4, observation 5. So you add up all of the x's from I equals 1 to n. N is the total number that you have, and you divide that by n, the total number that you have. But this equation just says add up all the x variables, all of them from the beginning to the end, and then divide by the number that you have. This equation is basically what you just said. You add them up and you divide by however many you have. Sometimes students get scared by the equations, which is why I will always give you the equation last. Because it's more important for you to know what's going on and to know how to do it than it is for you to recognize the equation. I'm going to give you a test over this beginning material, and on that test I'm going to ask you to calculate the average value, the variance, the standard deviation, the standard error, and a 95% confidence interval, and I'm not going to have the equations on the test at all. For two reasons. One, I don't care that you can write the equation. I just don't care about it. Two, if you don't know how to do it, the equation, looking at the equation, is not going to save you. And three, I would rather you know how to do it and be able to generate the equation later if you need it, but I don't want the equation to frighten you and confuse you when you're on a test. The thing to do is to learn how to do it. So this is the sample mean. This is the first thing that you need. This is the location parameter. This tells you where the sample mean is pointing to in terms of the population mean. It's not the population mean, but it should be in the neighborhood of the population mean. What we need to know now is how big is that neighborhood? We're in theory trying to estimate the population mean by taking some samples to generate a sample mean. The sample mean is an approximation of the population mean. It's in the neighborhood of the population mean. Now we need to know how big is the neighborhood that we're looking at. So the next thing that we want to do is we want to calculate the sample variance. Does anybody know how to calculate sample variance? Yeah, Claire.
Each of the samples and subtract
Yeah, okay, good. So what Claire just said is we take the original observations, these are the original observations, and we subtract the sample mean. We want to know how far do each of these data points differ from the location parameter. Well, in this case, this would be -4, -2, 0, +2, and +4. When we add all that up, what do we get? We get a 0. What that 0 implies is that there's no variation here. Is there no variation here? No, there's variation here. We've just calculated things in such a way that it sums to 0. Because if you think about it, within a sample, we have an observation here, an observation here, an observation here, an observation here, and an observation here. We average all of those up. We find that the sample mean is here. The sample mean is always going to be in the middle of the density of your sample. That's the nature of the mean, such that there are going to be as many points and distances away from the mean above the mean as there are below the mean. So the difference between the mean, the sample mean, and this observation is 0. This is +2. This is +4. This is -2, -4. They balance one another out. This -4 cancels that +4. This -2 cancels that +2. So if you just sum up those deviations, they add to 0, and they will always add to 0. So what you have to do is you have to get an idea of how far away they are from the mean that causes them to not cancel one another out. How can we accomplish that? Yeah.
Maybe like you don't include the mean and you take like the average distance. So you average like 2 and 4, -2 and -4.
You're approaching it. So it does involve an average. You're going to calculate an average of a sort. What's the easiest way to get rid of negative numbers? You could take the absolute value. You could also square it. What we do in statistics is we actually square it. Both of those would be appropriate. But one of the things we can do is just simply square it. This would now be +16, +4, 0, +4, +16. This was the deviation from the mean. Deviation from the mean, deviation from the mean, deviation from the mean, deviation from the mean. Now we've taken those deviations and we've squared them. This then is the squared deviation from the mean. We can add all of those up. 16 and 4 is 20, that's 40. And we can divide by the sample size minus 1. The reason that we divide by the sample size minus 1 is because this new measure, this variance that we're measuring, is actually using an estimate. The estimate that is using is this estimate here. So we've already used up some of our information to estimate this number here, which is the mean, which we then use in this calculation for the variance. So as we use up information, we take away sample size. Each time you use an estimate, you take away sample size. So in statistics, there are a bunch of things that we can do to quantify a distribution. The first thing we can do is we can calculate the mean. This uses up 1 degree of freedom. And so in the mean, the degrees of freedom that we have in the numerator, the sample size that we have in the numerator, is the total sample size. But to calculate the sample variance, which is an S with a squared above it, we're relying on an estimate that was based on the full data set. Because that estimate is based on the full data set, the denominator for division here is the sample size minus 1. This now tells us where is the mean, but it also tells us how spread out the data are. There's another characteristic called skew. Skew is the degree to which the distribution looks like this, or the distribution looks like this. This is positive skew because the tail is out to the positive side. This is negative skew because it's out to the negative side. Skew relies on 2 parameters to estimate skew. The parameters that you need to have already calculated in order to calculate skew is the mean and the variance. So now you've used up 2 pieces of information from your original data set. So the denominator for skew is in minus 2, et cetera, et cetera, et cetera. The next thing that you can calculate is something called kurtosis. How flat is the distribution versus how peaky is the distribution. Guess what? To calculate kurtosis, you need the measure of the mean, you need the measure of the variance, and you need to know how skewed your distribution is. So kurtosis is in minus 3. Every time you rely on a new estimate to calculate something new, you take away a piece of information because you're solely using up all the information that your data set has in it. So in this case, we would divide this by 4 rather than 5 because to generate sample variance, we're relying on one estimate already. So we take away one of our sample size. So this would give us a sample variance of 10. So in this case, the mean of this sample is 6. The sample variance is 10. What did we do to generate the sample variance? Well, we took each x value, we subtracted the mean from it, we squared it, and then we added all of that up from the first value to the last value, and we divided by the sample size minus 1. Another useful thing to do, yeah.
Is that the standard deviation then?
No, this is actually the sample variance.
Sample variance.
Sample variance. It is S squared. I'll explain to you why it's S squared here in a minute. Another thing that I find useful that for people doing this for the first time is it's always useful to just write out in words what the equation means. Subtract the mean from the data for all points. Boom. That's what's inside the parentheses. Square that. Add that all up. Divide by the sample size minus 1. This numerator is the sum of the squared deviations from the mean. The S here stands for sum. It's the sum of the squared deviations from the mean. As we move forward into talking about analysis of variance and regression and things like this, we will repeatedly see this thing called SS. Whenever you see SS, it's simply referring to the sum of the squared deviations from the mean. So SS means the sums of the squared deviations from the mean. When you look at an ANOVA table, we'll see it when we get there, that's one of the first things that you calculate when you're doing an ANOVA, is the sum of the squared deviations from the mean. Different variations on which deviations you're talking about, but ultimately, that's a really important thing that you calculate anytime you're testing to see if two populations or two samples are different from one another. Another important concept to think about is, I erased it, I'll put it back. These are the data from this example. The mean is here. The distance between this and this is plus 2 plus 4, minus 2, minus 4. These distances, the distance of each of the data points away from the measure of central tendency, in this case the sample mean, these things are referred to as residuals. And the residuals have the value attached to them. Because some residuals are above the mean, some residuals are below the mean. What we're basically doing here is we're basically taking the residuals and squaring them. You will see that I use the term residual over and over again as we once again get into testing, doing hypothesis testing. But when I talk about residuals, I'm just talking about what's the difference between the average and the data points. Some of them are above the average, some of them below the average. How far away from the average are they? But one way of thinking about what's inside of here is these are just residuals. We take the residuals, we square them, add them all up, divide by sample size minus 1. How do I know the equation? Obvious answer. I've taught this a gazillion times, and you teach anything often enough, you're going to learn the thing that you're teaching. The best way to learn a topic, teach it to somebody. But how did I learn this equation back when I was an undergraduate? I know the equation. Why do I know the equation?
For many years.
I've taught it for many years. That's the easy answer. I understand how it works. I understand this. Because I understand this, I can then do this. And that's how you should do it. Understand how it works, practice how it works. Once you know how it works, two things, you don't need this anymore. But if you ever need it, it's going to be there because this is just the formal way of writing those four statements. Questions about sample variance and how to calculate it? Okay. For this sample, this was 6, this was 10. You asked about standard deviation. Standard deviation is just S. This is really easy. S is the square root of S squared. So this should not be any problem to anyone. And at this point, now I'm going to have to get a calculator because I cannot do square roots in my head. I can do lots of math in my head. Square roots are not among them. I rearranged my phone over the holiday. And now I cannot find math. There's math. Square root of 10 is 3.1623. Nothing mysterious about standard deviation. This is the sample mean. Sample variance. Sample standard deviation. Why am I putting sample in front of each of these? Yeah.
It's not the population.
It is not the population. We're using a sample to tell us something about the population, but ultimately this is a skewed view of the population because we don't have the entire population in these calculations. So in all of these cases, we're using the sample to extrapolate to the population. And here in a minute, we are going to make that transition from talking about the sample to talking about the population. But remember, what we're doing is we're using the population. We're trying to get a picture of the population. We're getting that view of the population through a sample. And ultimately, we're going to make decisions about the parameter that we generate from that sample through the distribution of sample means. So in order to do that, we have to make that transition. And that transition occurs when we calculate the next thing on our path to figuring out what the sample tells us about the population. So we need the standard error of the mean. And this is done by basically taking the standard deviation the sample standard deviation and dividing it by the square root of sample size. So in this case, it would be 3.1623 divided by the square root of 5. So we need to know the square root of 5. Square root of 5 is 2.2361. So this is 3.1623 divided by 2.2361. You get 1.414? Is that what you guys got? Anybody get something different than that? Okay, cool. So why are we calculating the standard error of the mean? We want to know how this mean compares to a distribution of sample means. That's how we get the connection back to the population. That population has a distribution of sample means if we go and we repeatedly sample that population. All we have in the sample is the sample mean to rely on, so we need to relate that sample mean back to the population, but we can't go to the population directly. The only thing that we know from the central limit theorem is that if we sample that population over and over again, we'll get a distribution of sample means, and that distribution has a normal shape and it has a certain amount of spread, and that spread of that distribution of sample means is ultimately determined not by the inherent properties of the population itself, it's determined by how big our sample size is. The bigger our sample size is, the narrower that distribution of sample means is. Now that we know the relationship between sample size and the spread of the distribution of sample means, we can now figure out how wide that distribution of sample means is, because this is a sample-specific measure of spread. The original sample was 2, 4, 6, 8, and 10. If the original sample had been 2, 6, 10, 14, 18, that's a wider spread, which would make the variance bigger, which would make the standard deviation bigger, which would make the standard error of the sample mean bigger. But in both cases, these have a sample size of 5. So the confidence interval that we calculate for this particular mean is a measure not only of the sample-specific measurement of spread, but also a measurement of spread that is independent of the sample. It has to do everything with the sample size. So to figure this out, we have to go and find something called a t-table. This is the student's t-table. Anybody know why it's called the student's t-table? Student's t-table was invented by a statistician who worked for Guinness Brewery in Ireland. Guinness is a famous Irish beer. He was tasked with the job of basically doing statistics on Guinness production and things like this. And in order to do this, he needed to have some way of measuring not only the location parameter, but also the spread of the data, because beer production, like anything else, is naturally variable. And so he basically came up with an idea about how sample size affects, once again, the width of the distribution of sample means, and he quantified that by basically relating sample size to the spread of the distribution based on how confident you want to be in where your population mean is. And he generated this and thought it was a pretty good idea, wanted to get it published, but his agreement with Guinness was that you couldn't publish trade secrets at Guinness, and they considered this a trade secret. So he made up a name. I forget what the initials were, but the last name was Student, and he published it so that it would be available to the broader community. And so student is the nom de plume of this Guinness employee who invented the t-table, and so it's called the student's t-test because the original publication was published by a guy named Student. But what it basically says is, at the top here, it asks you, how confident do you want to be in your measure of including the population mean in this estimate? And so that's a level of alpha at the top. And remember, alpha is the type 1 error rate. It's the chances of saying that two things are different when in actuality they're not. And as you reduce your chances of saying that two things are different when they're not, alpha gets smaller and smaller and smaller. This is the distribution of sample means. Normally, we want to include 95% of the sample means, which means that there's 2.5% of the sample means out here, 2.5% of the sample means out here. And so alpha divided by 2 is 2.5, alpha divided by 2 is 2.5. So these two combined end up being 5%. This is what we call a two-tailed parameter. For this particular table, you see that there's 0.0005, 0.05, 0.01, 0.025, and 0.005. And you're going to see those headings at the top of every t-table that you ever look at. But the question is, if your alpha level is 0.05, do you rely on the figures in the 0.05 column, or do you rely on figures in the 0.025 column? Well, if your sample is infinite in size, 5%, which means 95% of the confidence interval, 95% of the sample means, 95% of the sample means is within 1.96 standard deviations of the distribution of sample means. So to find the right table, the right column in the table, you need to go down here to infinity and find 1.96. This is the column that you want to read, and you see at the top it's 0.025. So in this particular formulation of the table, 0.025 is the area under the curve split in two, rather than combining those. And different people will do it different ways. It just depends on the table that you're looking at. So you should always look at the table, go to the bottom and figure out, is this 95% confidence interval, or is this the 95% confidence interval? Because one of them is 0.05 at the top, one of them is 0.025 at the top, but the one that you're looking for is the one that is 1.96 if you have an infinitely large sample size. Luckily in this table, they also tell you the size of the confidence interval. 99% confidence interval, 98%, 95%, 90%. You're calculating a 95% confidence interval, which is an alpha level of 0.05. So what you do is you then say, well, I have 5 samples. Because you're calculating the confidence interval for a mean, you had to estimate that mean in order to do all the other calculations that you need to do this. So your degrees of freedom is always the sample size minus 1. So what you would do is you would go over here to sample size, to degrees of freedom of 4, come over to the 0.025, and you would find a t-statistic at an alpha level of 0.05 and degrees of freedom equal to 4 is 2.77645. And that's the t-statistic that you need to calculate a 95% confidence interval. So to calculate the 95% confidence interval is you need the standard error of the mean And you need to multiply that times the t-statistic for your particular alpha level and your degrees of freedom. So in this case, it would be 1.414 multiplied times 2.77645. .414 times 2.77645. That is 3.92. This then gets added to the mean and subtracted from the mean. So if our mean is 6, the range of our confidence interval would be 6 plus 3.926 and 6 minus 3.926. This is either, that's 9.926. This is a little more complicated. 6 minus 3.926 is 2.047. So the confidence interval you could draw like this. If we have a number line, the average is here, and we would have to go up to 9.926, up almost all the way to 10, and down almost all the way to 2. And this basically includes the mean, and this is the 95% confidence interval. So what does this mean, the 95% confidence interval? This is how you calculate it, but what does it really mean? Yeah?
It means that we're 95% confident that the true mean of the population falls within that data range.
Yes, that's one way of thinking about that. That's a totally correct thing. That's the thing that you will see in dozens, hundreds of statistics textbooks, but that's not the only way to think about it. What's another way to think about it? That's maybe more useful. Seldom are we actually trying to estimate the population mean. What are we usually trying to do? We're usually trying to tell if one mean is different from another mean, isn't it? So what does this tell us about the distribution of sample means? Yeah. Flip that on its head. Turn that around, do just the opposite thing.
So if the population doesn't fall inside of it, the central mean isn't from that?
So we're using the sample to talk about the distribution of sample means. This is a 95% confidence interval of the mean. What's inside of there? Sample means are inside of there. How many sample means? Most of them or hardly any of them? Most of them. If we go to this population, so let's say that there's a population out here, and we will just we'll look at this population, we'll say that this population is Q. We go to this population Q once, and we pull these 5 numbers out of it. That generates this mean, this variance, et cetera, and generates that 95% confidence interval of the mean. If we throw those numbers back in here, go to Q again, pull that out, calculate a mean, pull 5 numbers out again, calculate a mean, pull 5 numbers out of that again, we create a distribution of sample means, and 95% of those sample means will fall within this range. So you can think of it as there's a 95% chance that the population mean is in here somewhere. Population mean could be over here somewhere. Population mean could be over here somewhere. And that's useful if what you're trying to do is estimate where the population mean is. But oftentimes we just don't give a damn where the population mean is. We want to know, is this sample mean different from another sample mean in most cases? Well, in that case, what we can say is, this is the sample mean that we observed. If we went and got a bunch of sample means of the same sample size out of that population, some of them would occur here, some of them would occur here, some of them might occur way out here. But if we went 1,000 times to that population and pulled out sample means, each sample mean based on a sample of 5, 950 of them would be in here, 25 of them would be somewhere out here, and 25 of them would be somewhere out here. Therefore, if we know what this mean is, and we want to compare it to another mean, the mean of sample 2, all we have to know if these are different is, does this mean fall inside of that interval? In which case we would say that we drew those two means from the same population, Q. Or does this mean fall outside of that range, which would then tell us we didn't draw that mean from population Q, we drew that mean from population P or R or S or T. Your answer wasn't wrong, your answer is just not as useful as a different answer, because oftentimes this is what we're trying to do. Say, could these two means have come from the same population, or is it more likely that they came from different populations? If I ask you on a test what a 95% confidence interval means, you give me that answer, I will count it correct. But this is maybe a more useful way of thinking about it. Difference between correctness and usefulness. This is the only reason that we calculate 95% confidence intervals, is because we want to make a decision about this distribution of sample means. If we didn't care about comparing means to one another, there would be no reason to go through all these calculations. The only reason we do this is because we ultimately want to be able to do this. Questions? Yeah.
Why does it say that the 0.05?
Because this is the alpha level, and in this case, 95% of the population lies in the middle, which means 2.5% lies on this side, 2.5% lies on this side. That's a total 5%. So you can ask a question. This mean could lie outside of this 95% confidence interval on the high end, but this mean could also have been on the low end. So you take that 5% and you split it between the two tails of the distribution. If your question had been, is this mean bigger than this mean? You would have taken all that 5% and you would have dumped it into one of the tails. You would have dumped it into the upper tail. And then that would reduce a little the distance that you have to come out here. Because all of this probability would have been dumped over here, drawing this down. And so you would have had a 5% confidence interval. This, you only have to go out to 1.64 to see the difference, because you have a directionality to what you think the answer is. You suspect, for whatever reason, that this mean is bigger than this mean, so you can put all of that probability, your type 1 error rate, into one tail rather than two tails. So that's the reason for that. Now you need to make that decision before you go and gather your data. So if you think, let's say that you are a medical doctor, you're interested in fitness, and so you have a bunch of people who are all professed couch potatoes. They sit around watching Netflix all the time. You randomly assign these people to 2 treatments. Half of them get to continue being couch potatoes. The other half get engaged in CrossFit for 6 months. and then you measure what their fitness levels are at the end of that 6 months. You're not just looking for any difference. You're interested, more than likely, are the CrossFit people in better shape than the couch potato people? You shouldn't expect the CrossFit people to be in worse shape than the couch potato people. So that's the difference between a two-tailed test, where you could either be in better shape or in worse shape than the couch potato group. You actually have a directionality to your question. We think they're going to be better, so we actually want to test to see not if they could be better or worse, but are they indeed more fit, rather than either more fit or less fit. And that's why whenever you look at a T-table, you have to pay attention not to what is at the top as much as what is at the bottom. If you're interested in are they more fit or less fit, you would divide that 5% out into 2.5% tails. If you're only interested in if they're more fit, you would put all that 5% into one tail. Okay? And today we covered a lot of territory. We call this the difference between one-tailed tests and two-tailed tests, and that's an important concept that we'll revisit when we start doing hypothesis testing for real. But that's the crux of it. Questions? All right, that's all I have for you today. We will pick up here next time. Make up some data sets on your own. Just make up a set of numbers and practice these calculations to get used to them. You can look up a T-table almost anywhere on the internet. You'll find them. Once again, look for 1.96 as the area under the curve for which column you need to be looking in.